Hello, everyone. Hope you're doing well. Every now and then, I like to try and get some of the content for a given week down to just a couple of video lectures so that we can get to seeing where these things actually hold useful. In particular, I've mentioned that the reason for Fourier analysis really does stem from a lot of the things that we are talking about here. And it's the reason that we are talking about this stuff today is that it is the backing material for much of Fourier analysis. And unfortunately, we don't get to go into much of those details in this class. Instead, what I wanted to do was say, okay, from the stuff that we've gone through so far, what are some applications of what we've been able to look through? Some of you might be on our applied track here through the graduate program and are kind of chomping at the bit, perhaps, and ready to see, okay, how can I take these items that I've been learning about, these kinds of spaces and things like this, and start utilizing them in things that I'm more used to? Whereas some of you, even those who are theoretically or education, pedagogically minded, are saying, how can I explain to somebody else the use behind the thing that I'm trying to help them understand? Now, not everything in mathematics needs an answer to that question. Why is this useful? And perhaps you have, if you are an instructor of some sort, found nifty ways to get around that question here and there. Or maybe you found ways to directly say this is connected to this other thing that you might learn about later, and you can help kind of tease them along in that sort of perspective. But I want to also be motivating in that sort of way and say the question that we suppress within ourselves, the why are we learning this material? I think it's worth every now and then giving it a bone. I think it's worth saying we can find something that is useful here. And the great thing about analysis is there's so many directions that we can take in terms of applications. We've already seen so many things that are like, wow, that is cool, or that broke my understanding of what that was before, and I am surprised and in awe of that. We're going to keep going in this direction in order to solve some ODEs today using some notions of fixed point theorems. We'll need to talk about those theorems first before we get to how that can be applied in the terms of ODEs. But today we'll go ahead and do a little bit of a big brush up there. Some of the stuff in this material that we're talking about today, you might want to go back to your 689 or your 632 course, whichever one it was, something that you've already taken that is kind of helping you out with differential equations, to look back and see the ways that we talked about equations there and how you solve things like that. But what we're doing today is not going to require any of those sorts of methods or materials. Instead, we're going to talk about how you can solve ODEs of particular type by using this sort of process of a fixed point theorem. Let's go ahead and talk about what fixed points are real quick. Let's say that I am plugging in points into a operation. Maybe it is multiplying it through by the matrix 9/10 times. You might be familiar with this other matrix here. This is the rotation matrix by the angle pi over 4. So you can think if I plug in a vector like 1, 0 in for here, and I say I want to start seeing where this matrix goes, what happens to this vector if I plug it in through this matrix? Well, it should first rotate it counterclockwise by an angle pi over 4, and then should change its magnitude by a factor of 9 over 10. You can kind of see here what happened when I went through and plugged in the vector 1, 0 here. I went and got this value. I got 0.636 comma 0.636 when I went through and did that. Now, what's interesting here is that I could continue to now take that vector, the output vector from multiplying this matrix, and keep going. I could multiply it times the matrix A one more time and get this value right over here, which is A squared 1, 0. I could do this indeed for all of these other ones, and you can kind of see I've done this process a few times of finding A cubed, A to the 4th 1, 0. And what's happening is I am composing the matrix operator A with itself 2, 3, 4 times. And as I continue doing that, you can see here that I get a little bit of a spiral. And essentially, all of these points seem to be going toward a specific location. If I kept going here, I would be able to say, okay, here's my new spot, here's my new one. And then I can keep seeing where those points going as I continue to iterate the function of A. These points seem to be going somewhere with this point, and maybe it wouldn't surprise us to say that the points that these are limiting toward is the fixed point of this map. When I say fixed point, I'll actually define it likely later. The fixed point of a function f is a point and here this point F needs to be going from the same space to itself, is a point such that f of x equals x. So that point x is such that f of x equals x. The function f fixes this point if I go through and do that. And you can check here that the fixed point of A is the point 0, 0. Right, so A times 0, 0. If I plug that in here, then I'm taking that 0, 0, rotating it counterclockwise by pi over 4 and scaling it by 9 over 10. And that's just going to give me the vector 0, 0 again. Now note that a function can have more than one fixed point. Right? And so you can take that to be, for example, consider a matrix A with eigenvalue of 1. Notice that the matrix that I gave here had no real eigenvalues. Even if it did, the 9 over 10 would take things that had like eigenvalue of 1, perhaps in that matrix, and scale them down. But you could consider replacing the matrix A with something with an eigenvalue of 1. Then any eigenvector corresponding to that eigenvalue so corresponding to an eigenvalue of 1 is a fixed point. If you plugged in that value, you would get A times V is equal to V. And that's exactly what it means to be a fixed point. A function can have no fixed points. And that can be things just as simple as f of x equals x plus 1 from the reals to the reals. Something like this shows us that you could have no fixed points for a given function. So there are a lot of different options to choose from in order to say how many fixed points there are for a given function. Some have more than one, some have no fixed points, and this one that we saw, this example, is one that has exactly one fixed point. You might be familiar with this notion if you remember us talking about equilibria for a given function, especially in terms of differential equations. Discovering equilibria for that particular set of systems is something that's very useful for us. This is something we talked about back in 632/689 if you took that intro course. Otherwise, we'll talk about it a little bit later. Now, the matrix A that we gave above is an example of a contraction going from R2 to R2. A contraction in a metric space is a function such that the distance between any two y values of that function is less than or equal to s times the x values of that given function. So think, for example, this is kind of like taking something like an isometry and shrinking it down a little bit. An isometry function had it being the case that d f of x comma f of y was equal to d of x comma y. Whereas a contraction is something a little bit stronger. It's saying that you need to be able to take the distance between f of x and f of y, and not only make it smaller than the distance between x and y, but make it smaller than some factor of the distance between x and y. Because here, s is going to be some value that's in between 0 and 1. Technically, yes, no, actually, yes. So s is going to be a value in between 0 and 1. So note the distance between our points in the previous picture are getting closer and closer to one another as they move around. Namely, the distance between the y values of these points, right, is different than the distance between any two given x values. So if I think about what's happening when I'm plugging in this point and this point, then that's going to get closer and closer if I had plugged in this point and this point. That distance between the blue points is going to be smaller than the distance between the red points. That's exactly what we mean by a contraction, is that as you continue to plug in more and more, they continue to get closer, the y values get closer and closer to each other. Not all contractions are linear. That's something to note, like matrices are, but linear contractions make very useful pictures, which is why I used that on the previous slides. So there's no linearity required. So that means I don't have to have a matrix as the thing that I'm saying is linear. It could be something, or rather something that is a contraction. It could just be something else. These points are also getting closer to a singular point, which we could define to be, if we're familiar with this terminology, the equilibrium of the difference equation y sub n plus 1 equals f of y sub n. Another way to say that is just a fixed point of the function where f of a is equal to a. So if you're familiar with difference equations, maybe this is useful to you, or maybe we'll just go ahead and keep talking about this in terms of a fixed point. We're soon going to claim the following, that every contraction has a unique fixed point. Notice we've said that some functions have more than one, some have none. We're going to say that every contraction has exactly one fixed point. Our proof is going to start by, kind of like how we did in our previous slide there, constructing a sequence of this form. F composed with itself n times of x, which is, you can see here, this kind of dotted place where the composition takes place n times. Compare this to multiplying the vector 1, 0 by powers of a, kind of like multiplying, composing it with the function a over and over again. Then we'll show that since f is a contraction, this sequence is Cauchy. Remember, we use the fact that these points are getting closer and closer to each other as they move along, and hence these should be getting to be a Cauchy sequence, and hence they should converge whenever our metric space that we're working inside is going to be a complete space. We will then show that the limit of this sequence is the desired fixed point. And that's exactly what Banach's fixed point theorem says. Let's assume that you have capital X here. Let's assume that capital X, D, is a complete metric space, and that they have a function which is a contraction going from that complete metric space to itself. Notice it wouldn't make sense to think of it going between two separate metric spaces. Then composing this function might seem a little bit tricky. Then F has a unique fixed point A. No matter which starting point x naught that we choose, the sequence that consists of compositions of the function f with itself n times, starting from the point x naught, converges to the point A. Let's go through this. There's a couple of slides to this one, so let's kind of first break it apart into different pieces. We want to say that there's a unique fixed point. That means that there needs to be exactly one fixed point. So first, let's show it can't have two. Let's start by saying A and B are any two fixed points of f. Notice here I'm saying they might be equal, they might not be equal. We're going to come to the conclusion that they in fact are equal, so that any two fixed points I might say exist for my function f, they must be equal, meaning there cannot be two unequal or distinct fixed points for the function f. Well, then the distance between A and B, since A is equal to f of A and B is equal to f of B, since there's this equality between there, that's the same thing as the distance from f of A to f of B. Well, then we can use the fact that f is a contraction and get this less than or equal to sign to get that this is s times the distance from A to B. Notice now that I have that the distance from A to B is less than or equal to s times the distance from A to B, where s is that contraction vector. Remember, s here is in between 0 and 1. Well, the only way you can get this inequality to hold is if the distance from A to B is equal to 0, because s is only going to scale it down a little bit, right? Since the distance is if the distance is a positive number. The only chance is that the distance is exactly 0, which means that, in fact, the two fixed points that we started from are, in fact, equal to each other. Now let's get to this sequence. Here again, x sub 1 is the sequence that is just plugging in x naught into the function f. x2 is, you could write it either as f of x1 or as f composed with f, plugging in x naught. And then x sub n is composing in the nth n times f of x naught, and writing recursively, we can just write x sub n plus 1 is equal to f of x sub n. If we take the limit of this equation, then we will find that this is exactly the point that we're looking for. So let's see if we can take the limit of this equation. That'll be what the next slide is going to be about. So let's say that we've gone through the next slide and shown that we can take a limit of this sequence. Then if we do so, then the limit as n goes to infinity of x sub n plus 1 is the limit as n goes to infinity of this f of x sub n. It's going to turn out that a contraction is a continuous function. That's going to be an exercise for you to go through and look at. So that means that we're going to be able to actually turn and bring the limit inside of this function, f of the limit of as n goes to infinity of x sub n. Notice, by the way, that this is now the same limit on the inside and on the outside of this. Namely, the limit as n goes to infinity of x sub n is the same as the limit as n goes to infinity of x sub n plus 1. You're just one step farther along the same sequence. Both of these limits are the same, so we can call it a. So writing this equation again, A is equal to f of A. This means that A is going to be a fixed point. Now it remains to be seen that this x sub n that we formed is actually a Cauchy sequence. So let's talk about that next. Here is the set of inequalities that shows us that this is going to be a fixed point. Notice here we're going to use a few things that we've talked about in terms of series, namely talking about finite series and finite series, or maybe just finite sums at that point, and talking about how these sums can be formed with geometric and how the limits of these can be formed. So we're going to be doing some of these things in this sequence of inequalities. We're also going to use triangle inequality for metric spaces. So all of the things that we've learned are going to kind of get compiled here in this part of the proof. Let's start by saying that x sub n and x sub n plus k are two elements of our sequence. The only reason for writing n plus k here instead of the value of m is to emphasize that n plus k is k terms along from the value of n. This establishes a few things. One, this value of m is greater than that of n. And that's without loss of generality. If n had been greater than m, we would have just switched their roles in the Cauchy definition. The second thing is this. I also know that they are a distance k away from each other. Since that distance k is arbitrary, then that's okay for the definition of Cauchy as well. I'm just saying that you can have a point n past the cutoff point, n plus k. Any value of k works. Just any place that you would like to go past that point, pick your x sub m to be at that point. So we're going to write dxn x sub nk in a way that only relies on the value of n. Now, once we do that, we're going to be able to show that this distance is going to be less than epsilon. Namely, that this value of k wasn't that important. It only relies on one variable here. That's how we're going to get to our cutoff point, is once we get this distance to rely on one variable. Many mathematicians like doing this. They like saying, okay, if I have multiple variables in my problem, how can I get this down to one? An example where we might see this is in the definition of, or in the proof of the theorem that a Cauchy sequence in R converges. That notion of a Cauchy sequence in R converging is essentially saying, okay, how can I get it so that I don't have to worry about this x of m anymore, right? And how can I worry instead about some particular limit in which these two things are approaching? So this proof strategy is to get rid of an unneeded variable. And that's exactly what we're going to try and do here. We're going to see if we can get rid of this variable of k. Well, to do this, we're going to need to do, well, quite a few things. First thing is we're going to need to use the fact that, well, I know things about dx of n and x of n plus 1 in this sequence because I know that these are related by the contraction factor. So why don't we take a look at it in terms of that first? Let's start by breaking up the distance from x of n to x of n plus k in terms of these kind of like step-by-steps in terms of the sequence. Notice that now I'm going to be able to use this distance shrinking whenever I plug something in through a contraction. So that's exactly what I'm going to do. I'm going to now plug things in terms of this contraction here. So this is, say, for example, the composing n times. This is plugging n into x naught into that function of n, f composed with itself n times, and then comparing its distance to the value of x1 plugged into the function of f composed with itself n times. And notice that I'm doing that with every single term that I have. I'm getting it back down just in terms of x0 and x1. Notice that the thing that's iterating is how many times I'm composing this function with itself. What's interesting there is that now I can use the definition of contraction. Since I'm composing f with itself n times, I can get that to be just a distance between x0 and x1 by just multiplying the outside by s to the n. That's a factor of s for each time that I'm composing the function f. Since I'm composing in the next term by n plus 1 times, then that's s to the n plus 1. And then finally, it'll be s to the n plus k minus 1 for the final factor. After that, I'm going to go ahead and do some regrouping. I'll have s to the n dx naught x1 times this finite sum, which I should be familiar with. 1 plus s squared plus all the way to s to the k minus 1. That's something that I can write like this. 1 minus s to the k divided by 1 minus s. Got to come back out and come back in so that that doesn't look like a pixel. And finally, the last thing I need to do is know that wherever the sequence approaches, it increases toward, and it's increasing toward 1 over 1 minus s. Notice that in this final expression, I have achieved my goal. which is that I have found via inequalities a way to get rid of the value of k that gives me something that goes to be pretty small. Indeed, what I'm left with is a constant in terms of the value of n, and S of n is going to converge towards 0. So for any given epsilon, there's going to exist a cutoff point n so that s to the power of n times 1 over 1 minus s times whatever this distance is between the starting 2 points is less than epsilon. Notice here, this distance could have been very large. This could have been 1 times 10 to the million, right? Or however big it needs to be. But because s to the n goes to 0, I can eventually get this value to be 1 over 10 to the 1,000. And then I can gauge the same thing by 1 over 1 minus s and continue to make s to the n smaller and smaller as needed so that this is eventually going to be less than any epsilon that I might choose beforehand. So for m being greater than n being greater than big N, this distance is going to be less than epsilon. And that is, we can conclude from that the sequence x of n is Cauchy. Now we can go back through that second argument on the first page. So now we have the sequence is Cauchy to say that it converges, hence because it's a subset of real numbers. And because this exists in the real numbers and is convergent, that point that it gets to, you could show that plugging that point back into the function gets you back that point itself using the limit argument, and hence that is a fixed point. And that's exactly Banach's fixed point theorem having to do with these contractions. Note that nothing here says we can explicitly construct the fixed point. We can certainly make an educated guess. We can iterate a function f a few times on any point and watch for when the points start to slow down. That's when we see where those points are heading, trying to maybe take a graph of what those points are. That's exactly what we did on that first slide. We said, okay, well, maybe I don't know what the fixed point is by looking at this particular function, but after plugging in a few points, I can start iterating it a little bit and see where the points are heading toward. And wherever they head toward is probably going to be my fixed point. It's kind of like circling the drain, if you know what I mean. So let's see if we can do that in some examples that are upcoming. But first, let's take a look here at showing that you can get a unique fixed point for a function f. Let's suppose that f is a function from a closed interval on the reals to itself that is continuous everywhere and differentiable on its interior points. And let's suppose further that the derivative, or the absolute value of the derivative, is less than or equal to a constant less than 1 for all values in the interior of its interval. Let's show that f has a unique fixed point. A few ways to do this. Unique fixed point would mean what? That you would need to find one, there needs to be exactly one unique fixed point. So it means we're going to need to show it has at least one, and then show that it has at most one, that it cannot have two. There's a few different ways to do this. When I give this one to my senior undergraduates, I usually have them use the mean value theorem or something like this to show that if you would have two fixed points inside of there, that they would end up having to be the same to some extent. Now, let's see if we can do this a little bit differently now that we know something about contractions. So let's see if we can do that. We know something about contractions, right? We are saying that the distance from a contraction is a function f such that the distance from f of x to f of y is less than or equal to s times the distance between x and y. A question that I think is worth asking is the function f that we have up here, is this f a contraction? Because if it's a contraction, then we can get to use this inequality for free. And using that inequality, we have exactly Banach's fixed point theorem. We're inside of a complete metric space, namely the real numbers, and we have a function from the reals to the reals that is a contraction. So it's going to have the unique fixed point A that I'm looking for. So let's see if we can answer that question. I'm not sure if we can. Well, the distance for us is going to be this, right? F of x minus f of y in absolute value. We want to show that this is less than or equal to some s times x minus y for some value between 0 and 1. It's exactly here in our definition as well. So I'll go ahead and write that. So how are we going to do this? I want to use the derivative to help me out here. So I know that I have this derivative that is going to basically impact my slope on this function. How am I going to make this connection? How about this? We have a function that's going from the same space to itself. It's going from a comma b to a comma b. We know that the absolute value of its derivative is less than or equal to alpha, is less than 1. And we know that we can say some things about what this derivative is. Let's start maybe here. We should be able to get that, well, how do we say that these two things are separate? I think this is a little bit of a tricky problem. Let's think about how to connect the derivative to values of the function. Let's see if we can use the fundamental theorem of calculus to help us out here. Let's say, without loss of generality, just to kind of help us out here, that x is less than y. Then I think that we can find f of y by using the integral to help us out. Remember, the fundamental theorem of calculus says this: if I want to find the difference between f of y and f of x, then something that I can do is I can say that this is equal to the integral from x to y of the derivative of this function, dt. So this is f of y minus f of x on the left-hand side, and this is equal to the integral from x to y of f prime of t dt. That's exactly the fundamental theorem of calculus here. Because we have a differentiable function on its interior, we know that we can apply this. Well, how is the integral going to help me? Well, I know something about this function that's here on the inside. The derivative function I know is less than or equal to alpha. So if I wanted to make a bound here, then this would need to be less than or equal to alpha times the value between y minus x. Well, if I take a look at what I have here, I think I've basically said what I needed to say. Namely, because I can now do the same thing from the opposite side to get, say, f of x minus f of y, so on and so forth. I guess technically I need an absolute value of alpha here to say this. Then I should be able to say that this is going to be, this results in the fact that the absolute value of this f of y minus f of x is less than or equal to the absolute value of alpha times y minus x. Let me go ahead and extend to that other part to get that other side of that absolute value, because I also know that this is going to be, well, greater than or equal to the following. So this is equal to this. So this is absolutely less than or equal to alpha times this. And this is greater than or equal to negative alpha times y minus x, or however else I want to say it. So connecting these two facts together should be able to help me. So go ahead and write that all in one line here. This should be less than or equal to negative alpha times y minus x. And this should help me out here. What tool am I using to help me get this other side for this alpha? Well, I'm using something like this. Here's where it comes from. I'm taking f of y minus f of x in absolute value and saying that that's equal to the integral from x to y of the f prime of t dt, this value right here. But notice that there is an interesting fact that goes on here. I'll be mentioning this later, which is why I'm kind of going into detail about this particular step, is that if I have the absolute value of the area underneath the curve, f prime of t, that's going to be less than or equal to xy, the integral from x to y of the area under the curve of the absolute value of the function f prime of t dt. You can kind of check out why this might be true. Notice that f prime of t might be going positive for some of its values and negative for some of its values. Whereas for the absolute value of f prime of t, the function is always positive for all of its values. The magnitudes, however, are going to be kept the same, so the areas above and areas under are going to be kept the same. Just with the absolute value, you're taking the areas that are underneath the x-axis and you are switching them to be above the x-axis instead. So whereas here, this area might be adding and subtracting different areas above and underneath the x-axis, this one is always going to be adding regardless of what you're doing. And that's exactly where I can say that this is equal to the absolute value of alpha times the value of y minus x. That's exactly saying, by the way, that f is a contraction, where s is equal to alpha. In which case, that should give us everything that we need. Okay, so using the fact that f is a contraction, we can then say that it has exactly one fixed point. So notice how we kind of connected here with the derivative. You might have had some other ideas looking at this one. You might have said, okay, well, I wanted to divide this by the absolute value of x minus y. John, would that have worked at all? Saying that that absolute value of f of x minus f of y divided by the absolute value of x minus y, is that less than or equal to s? Well, the limit of that is less than or equal to s. What you might have noticed there is that that kind of connects back to the definition of the derivative, the one where we say that the limit as x approaches y of f of x minus f of y divided by x minus y is going to be less than or equal to alpha. But that's only in the limit. That's not necessarily saying that for all of the values of x and y that you can choose, that less than or equal to thing happens. So in order to do that, we needed to, or to get the full veracity of what we were asked for in this problem to show that this question is a contraction, then we needed to use the fundamental theorem of calculus here. Let's go ahead and see this with another problem. This one I wanted to show because I think this is a really cool thing. Let's take the value square root of 2, which is a root of the function x squared minus 2. And let's find a suitable approximation for the square root of 2 by hand. Let's see if we can actually find what decimals that we need for the square root of 2 before we do anything else. First things first, I'm going to draw a picture. Here's our function of x squared minus 2. And let's start by plugging in a point that is rather close by for this function. Well, so the first thing we should be asking is, can we just iterate in a similar way to what we have going on here? Notice here that our derivatives, though, of this function, if we say capital F of x is equal to x squared minus 2, then the derivative of this function seems to not really suggest, actually, that we can find a good way to make this a contraction, even if we were to limit its interval to be just the set of points between 1 and 2. Because there, the derivative is going to go from 2 to 4. That should not really look like a contraction. If I map two y values through this function, they should be farther apart, in fact, than the x values are. So plugging them into the function f is not going to necessarily get us to a fixed point. But what we could do is this. We could start thinking about how can we take this function and make it closer to what I really want out of this function. This is what I have, but I would like this to eventually get to be the function f of x equals x. So instead of trying to solve the equation, where is f of x equals 0, I'm going to ask the question, where is, I should have put in a lowercase f here, my bad. I'm going to ask the question, where is this other function, f of x, equal to the function x? That's going to look a lot like a contraction once or a fixed point for that function, whenever I find it. Now, what I want to be a fixed point for this function, I want to line up with this function, f of x equals 0. So here's how I'm going to define my function f. I'm going to define f of x to be equal to the function x minus the function lambda times f of x. So x minus lambda times f of x. Notice that if I plug in an x point where f of x is equal to 0, then that's going to correspond to a fixed point of this function. So a root of f corresponds right with a fixed point of this little f. And that's the sort of thing that we are looking for. Now, what about the lambda? What is the lambda there for? Well, the lambda is there so that we can say that the absolute value of f prime of x is less than or equal to 1, so that we can go back through and say that we have a contraction, and hence that we can get a fixed point. What would be a good value for this lambda, so that the derivative of this function, which we know to be the absolute value of, we have just 1 here, minus lambda times 2x, like we saw right here before, how could we get this to be less than or equal to 1? Well, there's a lot about lambda values that could work neatly here. After we kind of do a little bit of experimentation, we can see that any value for lambda in between 0 and 1 would be fine here, except, well, we also have to take into account that x is going to be inside of 1 to 2 for us. So maybe it's not going to be that quite okay. Normally, I'd be thinking about x values in between 0 and 1, but here I notice that my x values are somewhere between 1 and 2. Here, I just know that the root that I'm looking for, I've kind of given it a little estimation, that my x values are in between 1 and 2. That should be the case for the square root of 2. It should be greater than 1, but less than 2. So I'm looking for a value of y, or looking for now a lambda that makes this true for all x in our region. Well, what's the biggest that 2x can be in this region? Biggest it can be is 4x. So I believe actually we should have been limiting our take any lambda so that it's in between 0 and 1/2. If we go ahead and remove the equality here, we're going to have something that's a bona fide contraction and instead just make it a less than. So let's make sure we're sticking away from lambda values of 0 and 1/2 here. So now what do we have? Let's take a lambda value here and say, okay, I'm going to plug in lambda equals 1/4, for example. And now let's take a look to see what we can do. I cheated and given myself a little bit more room here. Haha. So I found all of this stuff for the function f. I have found a good lambda value that allows me to make this function f a contraction. So I know now that if I just start plugging in points inside of this x region, then I'm eventually going to find a value that gets me closer and closer to the fixed point here. And remember, again, the fixed point of this function f is going to correspond to the root of big F. So little f is a contraction. Let's start plugging in points. So maybe what we'll do is we'll just do a little bit of an iterative technique. We'll take x and f of x here, where here, again, f of x is equal to x minus 1/4 times the function x squared minus 2. So if I started by plugging in 1, for example, I can see that what I'm going to end up getting is, well, something that gives us 1.25 after calculating all of that. Pretty sure that's right. Just checking one more time. Yep, that should be good. And then I can do it again, this time plugging in 1.25. Each time I'm plugging in what that is for this x value here, as well as this x value here. It should give me what? 1.25 minus, I should be getting what? 25 over 16. So this is going to be 1/4 times 25 over 16 minus 2. It's going to give me negative 7 over 16. So this will give me plus 7 over 64. And we're adding that to 5/4, which is 80 over 64. So this is going to be equal to 87 over 64. Now I've gotten a pretty good approximation of this in terms of a fraction. If I know how to approximate decimals for in terms of 64, then I can use that to get a better value there. But my next step would then be to continue iterating 87 over 64 in for here and continue to getting to what that value is down in here. Let's go ahead and check to see what 87 over 64 would be as a decimal. I'm just going to go ahead and get my calculator up here. 87 over 64 is going to give me the decimal, which is about 1.359. And if I just plugged in 1.359 in for this function, I could check out what that would be. I'm going to take this number and I'm going to square it. I'm going to divide it, I might subtract 2 from it, and then I'm going to take that divided by 4. All right, actually negative 4 in this case. Oops, messed it up. So I'm going to take 1.359 minus, I'm just doing this up on my computer here, 0.25 times, in parentheses, 1.359 squared minus 2. And what that's going to give me is, oops, I plugged in the wrong number. Subtract that one right here. So that should give me something like 1.397. I just plugged in 1.359 there. I didn't even plug in the whole decimal, and I'm still getting closer and closer to what I know the decimal for this should be. What I'm doing is I'm using an iterative or an approximating technique to get me closer and closer to the value of the square root of 2. And if I continue this process all the way down, then I would get to the square root of 2. So I can approximate or find a suitable approximation for square root of 2 just by plugging in these values here and doing it by hand, or just using a calculator to do this. So let's go through the steps of what we did just to do this, to make this happen. The first thing was we said for our function x squared minus 2, we calculate the derivative of the function, as that's going to be useful for us. Then the second thing is we associate root of function with fixed point of the function f of x, which is x minus lambda times capital F of x. 3, find lambda such that absolute value of f prime of x is strictly less than 1, right? For x values in test region. And here our test region can be 1, 2. It could have even been something a little bit larger. We could have done 0, 3. It just would have been a slower process to get there. The narrower my test region for where I want my x values, my root to be, the better I'm going to be able to choose my lambda to be. I can choose it to be a, kind of like a larger weight in my function, and the better my iterative technique is going to be. So if I had chosen, okay, I know that this value is somewhere between 1.25 and 1.5, that I could have made this process a little bit faster because I could have chosen my lambda to be a little bit larger. So that gives me this. And then finally, for step 4, iterate the process of finding any point x to start, and then plug in x, f of x, f of x, and so on and so forth, kind of making each f of x the new x value for the next space. Right? So that's kind of our step-by-step that now allows us to associate roots of functions with this process of calculating the fixed point of a contraction. Let's see another application here, one more widely used for fixed point theorems. And this is going to use especially the heaviness of the fact that the metric space things that we're doing don't just necessarily work on the real numbers, they also work on any given metric space. We're going to form a contraction between functional spaces now in order to try and solve this ODE. Now, first, before I do that, I want to go ahead and make a quick definition here, as this will be useful for us later on. Here's a quick definition. You may have heard of this one before. A function f is Lipschitz continuous. This is a form of continuity that's a bit stronger than continuity for a function. A function f is Lipschitz continuous if there exists a value of m such that the absolute value of f of x minus f of y is less than or equal to m times the absolute value of x minus y. So this is for a function going from the reals to the reals, to be specific. Now, this actually looks very familiar to us, right? This is a type of definition that looks like a contraction. In fact, if the value of m is less than 1, f is a contraction. So this is a little bit larger of a notion than that of a contraction. It can still be Lipschitz continuous and still be a contraction. You can use this definition to help you out. Remember, I said there would be an exercise to say that a contraction is continuous, and this definition can be a little bit of a connecting phrase. Of course, to do that, you would need to say a Lipschitz continuous function is continuous, but I believe that you can do that with this inequality here. So this definition says that a function is not only continuous, but that is also continuous kind of with respect to some sort of weight on how high the slope of the function could be. For example, the function y of x equals x squared, this is not Lipschitz continuous. Although it is a continuous function, it is not Lipschitz continuous because you can find values, y values for this function that are less than or equal to any number times the x values for that function. Essentially, take your x values that you're plugging in to go like maybe 1, then 2 and 3. And if you plug in the corresponding y values, even though the difference between the x values is staying at 1, the difference between the y values is going like 3, 5, 7, 9, so on and so forth, going past any value of m that you could put in, going off toward infinity. So that's the definition of a Lipschitz continuous function. We'll use that here in this process. Let's do a quick review here for what ODEs are. First order ODEs of the form fy prime equals f of xy are what we're studying here today. You might be familiar with a few of these. Things like y prime equals y has a solution to it. We're looking for all functions y such that when you plug in the y into this function, that you get something that is a true statement. So essentially, you're looking for all functions whose derivatives are themselves. So our notion should be that this is y equals e to the x. Oftentimes, when we're doing our solutions, we'll also say that it's okay if you have a scalar out in front of it. It's like c times e to the x. And yeah, that would also work. If you tried plugging that into this, you would also get something that satisfies. And that's because of the constant multiple rule for derivatives. Since differential equations only involve derivatives, no real integrals or stuff involved, even with these sorts of processes, you can see that you can always multiply a scalar times any of your general solutions to an ODE. Hence, you can always just put a constant out front of the function solution that you would end up getting. You also can have this y of 0 equals y naught, or an initial value given to your problem, and it just tells you, okay, if I wanted to solve for this particular constant c, how could I do it? Well, I know that when y is equal to, or y, when I'm plugging in 0 for this function y, so that is wherever I see an x, I'm going to be plugging in 0, then I can use this to go through and solve for c. For example, if I knew that y naught was equal to 2, then I would know now, based on this equation, that c times 1 is equal to 2, or that c is 2. And that gives me a specific solution to the general equations of solutions. So for example, if y naught is equal to 2, then I know that the specific solution is going to be 2 times e to the x. This is a specific solution to an initial value problem. Or an IVP. Whereas this right up here is a general solution to the differential equation. So our ODEs that we're going to be studying are of the form y prime equals f of xy with some initial value plugged into them. I'm about to show you an iterative process here that's going to plug in a function and get out a function. Let's say that I start with a function, and to not confuse it with y naught, I'm going to start with that function being y1. So again, here y naught is just going to be some scalar. So this is going to be some value in the real numbers, whereas these new y values that I'm going to come up with, these are going to be functions. And here's how I'm going to iterate this process. Starting with this ODE, I'm going to solve for y of x. This is probably the way that I first started trying to solve ODEs when I saw them. If I saw you had y prime on this side and you were solving for y, I said, okay, well, I'm going to get rid of the derivative by just integrating. We're going to take that naive approach here. We're going to just integrate y prime to get what y is equal to, and that's going to give us y of x. Now, the reason that this typically does not work is that, well, you've got y over here on the right-hand side, and that gets a little bit picky, right? Now that you have y on the right-hand side, how am I supposed to isolate y? I basically have a function that's given to me in terms of itself. And that's going to be a little bit tricky to solve for outright in terms of an explicit solution. And indeed, an iterative process, kind of like how we did with square root of 2, is not going to give us an exact or explicit solution. The process that we're going to take here is an iterative process that helps us approximate the solution. But if we integrate this right-hand side now, replacing x with a iterating or an integrating variable, t, so that we can integrate from 0 to x and not have any math police yell at us, then we're going to get the function y of x equals the integral from 0 to x of f of t comma y of t dt. We can plug in a starting function y sub 1 in for the right-hand side of this equation. If y sub 1 is close enough to our solution, or what we think our solution should be, then mapping it through this function here, the integral from 0 to x of f of t comma y1 of t dt, then what we're going to get out of that is another function, because we're integrating this and putting a variable back in, that variable being the function x. And that's exactly what we're going to call y2. y2, we're going to go through and map through, and we're going to just plug it into this y spot again, f of t comma y sub 2 of t dt. And what we're going to get out of that is a function y sub 3. All of these functions are not necessarily the answer to this differential equation. But if we have that the process that we're taking right here, namely if this function f, big F we could call it, which takes a function y and spits out the function integral from 0 to x of the function little f, our f, this being the derivative function that we got from up above, t comma y of t dt, this being so something from we'll say a sufficiently nice space of functions. We could say, if we need to, this is the space of smooth functions, which I'll write as C infinity, to itself. Then I can say, okay, well, then this is something that I could consider as a iterative process. This is a function that I could start asking, can I make this a contraction? If there is a contraction, then there's a unique fixed point, and any starting point that I choose, I'm going to eventually get closer and closer to the function that I'm looking for. Before I actually go through and show you the mathematics behind why a lot of this works, let's start by seeing some appropriate conditions that need to take place on the function f that we're using as part of this mapping that we're using here. So notice again that this mapping takes a function y, plugs it in as the second variable of the function f. Remember, this function f is a variable of x and y, and that's the right-hand side of this differential equation. This could be, just for example, integrating the function y if we're looking in terms of this equation right here. Then that function f needs to satisfy a few things. It needs to be so that t can be made a contraction. It needs to have a singular fixed point, otherwise by Banach's fixed point theorem, it cannot have a contraction. But we know that there are possibilities to have more than one solution to an initial value problem. So even if the function f is continuous, that's not nice enough. When I said we needed to be in nice functions, we needed this to be more than just a continuous functions. But it turns out that when we're in the theorem that we talked about back in Math 632 or 689, this existence and uniqueness of solutions theorem, then we have the unique solution that we're looking for. And we want to correspond that unique solution we're looking to as the unique fixed point of this contraction mapping, this capital F that we're coming up with. By the way, we could have actually replaced the differentiability of f with Lipschitz continuity of the function f, but we won't leave that. Well, that'll just be a little bit of a picky thing that we'll talk about later. Let's go ahead and see how this process works before we get into the mapping, before we get into the math behind why it works. So let's see it in this problem. Let's solve the initial value problem y prime equals 2x times the function 1 plus y. So in this case, our function is 2x times 1 plus y. So this is the function f of x, y that we're working with. Notice, first of all, that f is differentiable, and that, as given up above in our condition from existence and uniqueness, the partial derivative of f with respect to y, which is just 2x, is continuous. So we need f to be differentiable, so that's given to us up here, namely that f is continuous on some rectangle and that the partial derivative of f with respect to y is continuous. So we are good to go there. So we know that we can have a uniqueness theorem here and that we can get something that is of a form of a contraction. Let's see how we could go through and do that. Now, the mathematics above is going to tell us this. We need to look for functions that are nice enough, basically continuous functions, in going from c from 0 to some value of delta. And we'll be able to say that with nice enough differential equations, if something works inside of continuous functions going from 0 to delta, then we're going to have nice enough functions everywhere. A good place to start with this sort of iterative technique is going to be with the function 0. So let's see if we can start with the iterative process with phi sub 1 equaling the function 0. Let's just say that it's equal to the 0 function. Well, that's going to imply that phi sub 2 is going to be equal to, we're going to plug in phi sub 1 into this function. It's going to be going from 0 to x to t times 1 plus phi sub 1 of t dt. In this case, phi sub 1 is 0. So this is going to be equal to just the integral from 0 to x of 2t dt. And that's going to be equal to t squared evaluated from 0 to x, and that's going to give me x squared. That's now going to give me what I want to plug in for the function phi sub 3, which is I would like to now integrate 0 to x 2t times 1 plus phi sub 2 of t, which in this case is going to be equal to t squared. So I'm plugging in t, notice here, because that is now my integrating interval for this. So this is 1 plus t squared dt. So this is the integral from 0 to x of 2t plus 2t cubed. That's going to give me what? T squared plus t to the 4th over 2. And that's another, or rather x, I should say, because I'm plugging in x squared plus x to the 4th over 2. And if I continue this process all the way down, you'll see that I start getting a little bit of an iterative process, or an iterative sum that comes from this. Phi of 5, for example, after plugging in from these individual functions, if I plug in phi sub 5, that's going to be equal to x squared plus x to the 4th. And you'll see here that where this number comes from, if you check this out, you're going to get x squared over 4, x 4th over 2, plus you're going to get x to the 6th times. This thing is going to be divided by 2 in this case. And so I'm going to be getting that this is over 6 when I go through and integrate this. So I'll have my first function being x squared, my second function being x squared plus x to the 4th over 2, my third function being x squared plus x to the 4th over 2 plus x to the 6th over 6. Notice that I am approximating a function with these partial sums. What function could I be approximating with these partial sums is an interesting question. So to do that, I want to take a look at what these functions seem to be approaching. I seem to be getting a sequence here that looks something like 0, x squared, x squared plus x to the 4th over 2, x squared plus x to the 4th over 2 plus x to the 6th over 6. They seem to be approximating functions of something else. And I'm having a little bit of difficulty thinking about what it could be. Well, I'll go ahead and give you this one, but there's a notion here with Taylor series that might be useful here, is that this is very close to some Taylor series that I'm familiar with. You might know, for example, that if I take something like, let's say 1 plus x squared over 2 plus x cubed over 6, so on and so forth, that should give me e to the x. This looks very close to that, except that this looks like this is for e to the x squared more likely than not, right? Because if I plugged in e to the x squared in for x inside of this formula, I would have 1 plus x squared plus x to the 4th, which is x squared squared, divided by 2, plus x to the 6th over 6 plus dot, dot, dot. So if I wanted to figure out where this sequence of functions is heading toward, I would just subtract 1. I would just take the 1 and move it over. It looks like I have found what I'm looking for as far as my function here, e to the x squared minus 1. That this gives me what I'm looking for in terms of where these functions are approximating. You can actually go through and check this one yourself. You might notice this is a separable IVP, and you can use the ways that you've learned to solve differential equations from an undergrad level course or from our 632/689 course to figure out that this is actually a solution to this IVP. In fact, it is the solution to this IVP since we have a specific solution when we plug in y of 0 equals 0. But where did that come from? How did that work? How were we able to show that these things here were contractions? We just used a function that was nice enough to get us started, right? Just plugging in 0. And indeed, by the way, plugging in 0 here typically does give us a good enough starting points that we can eventually iterate to the correct solution. And in fact, I prefer that you plug in 0 for a lot of these to begin with, as it makes things a lot easier to know how to start, and then it just becomes a process of how to finish out. But where does that come from? What is that mathematics that's coming there and happening? Well, what we're doing there is we're using the fact that we are on this space C from 0 to delta, and we're using the infinity metric on that, taking it to be the maximum from 0 to delta, phi of x minus psi of x. Here, phi and psi are lowercase Greek letters that are being used to signify two given functions. So our goal is to show that if we go through and plug in t for this contraction here again, t is the function that takes us from a nice enough space like C infinity, for example, to itself. And the way that it does is it says, okay, I'm going to take that function y that you just plugged in here, and I'm going to integrate it going from 0 to x of f of t, comma, y of t dt. So this is that function t. So our goal is to show that this thing is for some contraction factor that exists between 0 and 1, basically to show that t is a contraction. One fact that I'm going to need is that this function f is Lipschitz continuous, and that's exactly this fact right down here that we talked about at the very beginning. But it turns out that showing that this thing is a contraction really only relies on the value of delta that you chose for how wide you want your continuous functions to go. And we can actually use this in the checks of everything. Notice that everything that we talked about today is going to come together. The fact that the absolute values can come inside of an integral, for example, is something we talked about near the very beginning of today. And that's using the fact that this absolute value of the area under a function is less than or equal to the area under the absolute value of that function. And that gives us absolute values existing inside of an integral rather than outside it. And knowing that this is a function going from here to here, and that this has a Lipschitz continuity notion on it, that's this one is here to say, is that we're going to reference this part later. That comes out with a factor of k, that factor being the Lipschitz continuity part of it. And then we're just going to be integrating something going from 0 to x from phi of t minus psi of t, which we can make an approximation of, saying that this is going to be less than or equal to x, however wide it is, the thing that you're integrating, times the highest possible that this function phi minus psi could go. If you have that this function phi minus psi looks like something like this, then you know that the integral underneath this curve is going to be smaller than, however else, the highest possible point that you could have said was the y value for that function. So something like this is what you end up getting, that this is the area of a rectangle containing the area under the curve phi minus psi. But we know that this maximum here is itself bounded, and that's because it's exactly the distance between phi and psi inside of this particular space. So to take a maximum now of x over both sides, we get that the distance from this point to this point in terms of our metric on C infinity, or rather just on C and that point, is less than or equal to k times delta times the distance from phi to psi. And if we choose delta, the kind of window there, to be something so suitably small that it's less than 1, then we get that t is a contraction, and that leads us straight to our solution. That is that there is a unique fixed point here, and that any point that we start from is eventually going to iterate to get us to whatever the function is that we're looking toward. And that is exactly what we did in our example beneath, looking at the function of e to the x squared minus 1 as our solution there. My advice here is to take this particular last part a little slowly. We are going to be seeing inequalities like these later on, especially again in that latter half of this unit. This sort of stuff we're not going to be doing a lot in our work, but we are going to see things like that happen later on. So let this be me kind of introducing you to the sorts of steps that you might see with functions and integrals and how all of these things interact, how we do areas of rectangles and things like this. Take this as an opportunity to look over it and try and understand as much as you can of this particular style of proof. You may not understand it all right now. You may not understand it a week from now, and that's totally okay. But by the latter half of this course, we're going to start seeing patterns of these sorts of things becoming a little bit more useful for us as we start moving along. But that'll do it for us today. We have talked a good bit about fixed point theorem, namely Banach's fixed point theorem. You may have heard of other fixed point theorems out there like Brouwer's and things like this. And typically these are not related to the fixed point theorems we're talking about here. This being just something that can exist in terms of any given metric spaces, whereas Brouwer is looking at a more topological sort of framework there. But here we've seen how fixed point theorems have applications in two ways. One, a neat way to approximate the root of a given function, like square root of 2, in a very appropriate way, and using iteration to help us out there, as well as to find answers to ODEs. which is again a huge component of where analysis is coming from, is to solve differential equations in any sort of perspective. And so if we are able to do this in terms of iterating functions like this form y prime equals f of x y, then we can now suddenly start finding out how to get to solutions in many in a very large class of ODEs. That having that on hand is huge for our being able to continue in that direction. But that'll do it for me today. Thank you so much. Have a wonderful day.